Hi everyone. In the last class, we have discussed about the classification of the spectrum of a bounded linear operator into three subsets of the spectrum, and we have also seen one example, namely the diagonal operator on L2 and spectrum of it. Today we are going to look at few more examples of operators and how to compute their spectrum using the classification that we did in the last class. Okay, so let us start with the right shift operator. So define R from L2 to L2 by R of x1, x2, x3 so on is 0, x1, x2, x3 so on for every xn in L2. This is the right shift operator. So we know that norm of this right shift operator is 1, and we also know that spectrum of any operator is contained set of all lambda in C such that mod lambda less than or equal to the norm of the operator. So this is mod lambda less than or equal to norm R, that is 1. So if you write D as set of all Z in C such that mod Z strictly less than 1, the open unit disk, then we can say that spectrum of R is contained in the closure of the open unit disk, that is nothing but the closed unit disk. Now we want to show that spectrum is exactly the closed unit disk. So claim spectrum of R is exactly okay. Now instead of looking at the spectrum of R, we also look at the spectrum of R star. It can be easily shown that spectrum of there is a relation between spectrum of T and spectrum of T star. So this can be checked easily. Let T be a bounded operator on H, then spectrum of T and T star is related in the following way. Spectrum of T star is exactly lambda bar, where lambda is coming from spectrum of T. The second one, spectrum of U star TU is exactly spectrum of T for any unitary operator U. So these are the simple results which we can prove by definition of the spectrum. Okay, now here if you use the result 1, we can instead of looking at spectrum of R, we can look at spectrum of R star, namely the spectrum of the left shift operator. Okay, so we have L is nothing but R star, and spectrum of L is set of all lambda bar, where lambda is coming from spectrum of R. Okay, now let us try to look at the set of all eigenvalues of L. So let us take lambda from the unit disk, then let us take the vector x as 1 lambda, lambda square, lambda cube, so on, so which is an element of L2. Then we have, if you look at Lx is nothing but shifting one unit to the left hand side. Let lambda, lambda square, lambda cube, so on. This is nothing but lambda times 1 lambda, lambda square, so on. This is lambda x, and we know that x is non-zero, so therefore we can say that lambda is in the point spectrum of L. Okay. So that means we can say that D is contained in spectrum of L. So therefore D is contained in spectrum of L, And we also know that spectrum of L is contained in the closed unit disk. This is anyway true by the earlier observation that spectrum of an operator T is contained in set of all lambda in C such that mod lambda less than or equal to norm T. So as spectrum is closed, so this also implies that D closure is contained in spectrum of L closure, that is contained in D closure, or we can say that spectrum of L is exactly D closure. Okay, so from this we can conclude that spectrum of R, so therefore spectrum of R, that is spectrum of L star, is lambda bar, where lambda is coming from spectrum of L. So this is the closed unit disk. So if you take lambda in the closed unit disk, lambda bar is also in the closed unit disk, hence this is nothing but D closure. Okay, so we have shown that spectrum of the right shift operator as well as the spectrum of the left shift operator is the same, and that is nothing but closed unit disk. Okay, now we want to look at other parts of the spectrum. We can ask what is the point spectrum of right shift operator. Okay, now let us try to look at for what lambda in C, that is in the point spectrum of R. Suppose lambda is in the, so let us look at R minus lambda I, whether that is 1 1 or not. So null space of R minus lambda I is set of all x in L2 such that Rx is lambda x. So here we can take x to be the sequence xn. Okay, so this is nothing but set of all xn in L2 such that by definition this is 0, x1, x2, so on, equals to lambda x1, lambda x2, so on. So if you look at this one, solve this equation. So lambda x1 is 0, lambda x2 is x1, lambda x3 is x2, and so on. We want x1 to be non-zero, so this implies lambda to be 0, and again when lambda equal to 0, if you substitute in this equation lambda x2 equal to x1, then we get x1 equal to 0, a contradiction. So therefore lambda is non-zero. Now once lambda is non-zero, so then we can conclude that x1 is 0. Once x1 is 0, this implies x2 is 0. Once x2 is 0, x3 is also 0, and so on. So that means there is no non-zero vector x such that Rx equal to lambda x. That means we can conclude that, therefore we can say that null space of R minus lambda I is 0 space. That means R minus lambda I is always 1 to 1 for every lambda in C. For every lambda in C, but lambda non-zero. Okay, so for lambda, okay, and for lambda equal to 0, then it's also 1 to 1 because right shift operator is 1 to 1. So we can conclude that this is for all lambda in. Okay, now we want to see whether this lambda is given any lambda in the complex plane that does not belong to point spectrum of R. Of course, we have to look at lambda in the closed unit disk only, because spectrum is exactly closed unit disk. Now we want to see if the point spectrum is empty, what are the other spectrums, residual spectrum as well as the continuous spectrum. So that is the next question. So what is sigma residual? Okay, so lambda is in the residual spectrum of an operator if and only if the operator is R minus lambda is 1 to 1 and range of R minus lambda I is not dense, or we can say that this is nothing but null space of its perp is not zero. That means null space of adjoint of R minus lambda I is L minus lambda bar I is not equal to 0. Okay. We know that for every lambda in C, R minus lambda is 1 to 1, but we want to see that for what kind of lambda null space of L minus lambda bar I is 0. Okay. Now we are looking at lambda in a closed unit disk. So whenever lambda is there in the closed unit disk, lambda bar is also there in the closed unit disk. Hence we can say that whether we look at lambda or lambda bar, it's not going to change anything. So let us look. The question we can ask is that for which lambda in D closure L minus lambda I is not 1 to 1. We have seen that when lambda is in the open unit disk, null space of L minus lambda is not 1 to 1, because null space of because of the point spectrum of L is exactly the open unit disk. So clearly we can say that this implies lambda in D. So this is true whenever lambda is in D. Now can we say what will happen when lambda is in D closure? Now let us take lambda in C with mod lambda equal to 1. We want to compute whether null space of L minus lambda is 0 or not. Suppose there exists x with x1, x2, x3, so on in L2, such that Lx equal to lambda x, or we can say that x2, x3, x4 is equal to lambda x1, lambda x2, lambda x3, so on. This implies that x2 is lambda x1, x3 is lambda x2, x4 is lambda x3, and so on. Again, this implies x3 can get lambda x2, but this is lambda square x1, and x4 is lambda x3, that is nothing but lambda cube x1, so on. So that means if x1 is non-zero, then the vector x1, lambda x1, lambda square x1, lambda cube x1, so on, this is in the null space of this is an eigenvector. This is a null space of L minus lambda I. So if I take x1 out, this is 1 lambda square lambda cube. This is in null space of L minus lambda I. But it has to be a vector in L2. So that happens when lambda is strictly less than 1. But we have taken mod lambda equal to 1. So this implies x1 is 0, since x1 into 1 minus lambda square. So once this is x1 is 0, so then the whole vector is 0. That means there is no lambda is not an eigenvalue. So this implies lambda is not in the point spectrum of L. So we have shown that the open unit disk is in the point spectrum of L, but the closure of the closed unit disk is the boundary of the closed unit disk is not in the point spectrum of L. So therefore we can say that point spectrum of L is exactly the open unit disk. Okay. So now we computed point spectrum of L. To compute residual spectrum of R. So we know that R minus lambda is 1 to 1 for all lambda, but we want to know what is null space of L minus lambda bar I when it is non-zero. So this is non-zero provided lambda is in the open unit disk. So we can say that, so let me say this is star, this is 1, this is 2, and this is 1. So from 1 and 2 we can say that we have residual spectrum of the right shift operator is the open unit disk. Now we know that spectrum of the right shift operator is disjoint union of point spectrum of R union residual spectrum of R union continuous spectrum of R. The first one we have shown to be empty set, second one is the open unit disk, but on the left hand side we have the closure of the closed disk. So this implies so we can say that D closure is D union boundary of T, and these sets are disjoint, so we can conclude that the continuous spectrum of R is exactly the circle. Okay. Now earlier we have discussed that the point spectrum of L to be the open unit disk and the spectrum is the full closed unit disk. Now we can easily find out. So exercise, find the residual spectrum of L and the continuous spectrum of L. We have to use the same method that we have used for the right shift operator. Okay, so this is about the right shift operator as well as the left shift operator. Next, let us look at a few more examples. Let us look at the multiplication operator. Let us take f to be a continuous function on AB. Define MF from L to AB into L to AB by MF at G is F into G for every G in L to AB. Okay, now we want to find what is the spectrum of MFF. Find spectrum of M. So to find the spectrum of M suffix F, we want to look at under what condition it is invertible. We know that a function is invertible, a continuous function is invertible if and only if it does not vanish at any point of the domain. So from this we can say that MF is invertible if and only if F is invertible if and only if F of t is non-zero for every t in the closed interval AB. In this case, MF inverse is exactly M of F inverse. Okay. Now if you want to find the spectrum, we have to look at MF minus lambda I. So then let us take lambda in C. Then we have MF minus lambda I. That is nothing but, so lambda we can write as MF minus M lambda into 1. 1 is a constant function. 1. So 1 at t is t. 1 at t is 1. For every t in AB. So this is nothing but M F minus lambda into 1. Okay. So MF minus lambda is invertible if and only if M suffix F minus lambda is invertible. That is if and only if F minus lambda is invertible. In that case, MF minus lambda inverse is nothing but M of F minus lambda inverse. Hence we can conclude that. So therefore minus lambda is invertible, is not invertible if and only if F minus lambda 1 is not invertible. So this is nothing but lambda is in the spectrum of MF if and only if lambda is in the spectrum of F. Is nothing but the range of the function. Okay. So that means, therefore we can say that spectrum of MS is exactly range of F. Okay. So this is about the multiplication operator. Next we can slightly generalize this example to a general setting. Okay, so let us start with X sigma be sigma finite measurable space, sigma finite measure space, and F is coming from L infinity of X sigma mu. So define the multiplication operator induced by F by MF is a multiplication operator from L to X sigma mu into L to X sigma mu divided by, defined by MF at G is Fg for every G is in L to X sigma mu. Okay, so we know that this operator is bounded and norm of MF is essential supreme of F or mod F. This we already know. Now we want to find what is the spectrum of MF. Okay, so to find the spectrum of MF, we will define another concept called essential range of F when F is in L infinity. the essential range. Okay, so let us take a function f from L infinity of x sigma mu, then the set of all lambda in C such that mu of the set f inverse of the ball centered at lambda with epsilon has positive measure for every epsilon positive, or this is also known as set of all lambda in C such that measure of the set of all x in X such that mod fx minus lambda strictly less than epsilon has positive measure for every epsilon positive. So this set is called the essential range of f. Whenever f is coming from L infinity, we can easily show that whenever f is a continuous function, the range and essential range are same, they coincide. So f is continuous, then we can show that essential range. So usually we write the essential range by this notation. Okay, so this is a closure because essential range is always closed. Okay, but range need not be closed. But when we define the function to be function on a compact set, then range is always closed for a continuous function. Okay, so this is the definition of essential range. Now in this case, for the spectrum of MF, we want to show that spectrum of MF is exactly essential range of F. So here we can write this is essential range of F. Okay, now let us look at the proof of this one. So let us assume that lambda is in the essential range of F. So then we have, for every epsilon positive, the measure of the set F inverse of ball centered at lambda with radius epsilon is strictly positive. So this is true for every epsilon positive. We can take epsilon to be 1 by n, then taking epsilon, so we can say that measure of the set F inverse of ball centered at lambda with radius 1 by n, this is positive. Okay, now we want to define, so let an be a subset of this set F inverse of ball centered at lambda with radius 1 by n be such that mu of an is an which is positive for every n. So choose a subset of F inverse of b lambda with radius 1 by n so that mu of an is strictly positive. So define gn as 1 by root an chi of an, the characteristic function supported on an, then we can show that mf minus lambda I at fn, sorry, at gn if you look at norm of the square, this is nothing but norm of f gn minus lambda gn square. This is by definition, this is integration over x f of p gn of p minus lambda gn of p modulus square d mu. But gns are supported on an, so this integration will be integration over n. Gn is nothing but 1 by an chi an, so we can get here 1 by an here we will get 1 by an integration over an mod f of p. Now gn at p equal to 1 when p is in an, this is lambda square d mu. Okay, whenever whenever lambda is in the essential range, then whenever lambda is in the essential range of the function, then the measure of this set f inverse of b lambda 1 by n is bigger than 0. That means f of lambda minus so when f of p, when p is in an, f of p will be in the ball centered at lambda with radius 1 by n. That means mod f of p minus lambda n, lambda will be strictly less than 1 by n. So this is less than or equal to 1 by an 1 by n square into mu of an, but mu of an and an are same, so this you will get 1 by n square, and this goes to 0 as n tends to infinity. So we got a sequence of vectors. We can easily check that norm of gn is 1. L2 norm of gn is 1 here. So we got a sequence of vector unit vector gn such that mf minus lambda at gn that goes to 0. So this implies that mf minus lambda I is not invertible. So if at all this is invertible, this has to be bounded below, but we have shown that we got a sequence such that mf minus lambda is not bounded below. So from this we can say that mf minus lambda is not invertible. So this implies lambda is in the spectrum of f. Okay. Now when lambda is in the essential range of f, we have shown that lambda is also in, so therefore we can say that essential range of f is contained in spectrum of mf. Now we show that whenever lambda is not in the essential range of f, then lambda is also not in the spectrum. So now let us take lambda which is not inside the essential range of f. Let lambda is not inside essential range of f. Then there exists a natural number n such that measure of the set f inverse of the ball centered at lambda with radius 1 by n is 0. By the definition of essential range, when lambda is outside the essential range, we can find some epsilon bigger than 0 such that mu of f inverse ball centered at lambda with epsilon is 0. But by the Archimedean property, we can always choose a natural number n such that 1 by n is strictly less than epsilon. So from that this follows. Now define G as 1 by f minus lambda into 1. Then we can conclude that G is the inverse of f minus lambda 1. So wherever the function is f of x equal, set of all x such that fx equal to lambda, that set has measured 0 by the above assumption, above condition mu of f inverse lambda 1 by 0. From that we can say that G is defined almost everywhere, G is non-zero almost everywhere, hence it is invertible. So that means whenever lambda is not in the essential range, G is invertible. That means f minus lambda is invertible. So therefore this implies that mf minus lambda I is invertible, because when we know that function is invertible if and only if the multiplication operator induced by the function is invertible. So this implies lambda is not in the spectrum of mf. So we can say that from these two arguments, the spectrum of mf is exactly essential range of Again, when f is a continuous function defined in a compact set, essential range and range are same. In that case, the multiplication operator reduces to the multiplication operator induced by a continuous function. Okay. So we have taken a function f in L infinity x sigma mu, and we have defined mf, which is a bounded linear operator on L infinity of x sigma mu. And here essential range is nothing but spectrum of f. Now we know that L infinity is also an algebra. It's a Banach algebra. In fact, this is also a C star algebra. Now as an element of the C star algebra, what is the spectrum of? So question is the following: what is spectrum of f when you take f as an element of the C star algebra L infinity of x sigma mu? In fact, we can show that. So let us try to look at this when f is continuous function defined in a compact set. That means when f is in C of k, spectrum of f is exactly range of f. Now with this analogy, we can easily conclude that essential range of f is exactly the spectrum of f when f is coming from L infinity. So check that spectrum of f is exactly essential range of f for f in L infinity of x sigma mu. Okay, so that means if this is proved, we can actually conclude that spectrum of f and spectrum of mf are same, that is essential range of f. Okay, so this is about the multiplication operator. We have already commented that multiplication operator is a normal operator, which is a prototype for all the normal operators. Okay, now let us look at one more important operator, namely the integral operator. Okay, so let us look at the Volterra integral operator. Okay, so define V from L to 0 1 into L201 by Vf at S is integral 0 to S f of t dt. So we have shown that this is a boundary linear operator. Now we want to find the spectrum of V. So the question is, what is spectrum of V? Surprisingly, it turns out to be that spectrum of V is exactly the set 0. So the claim is the following: spectrum of V is 0. Okay, so here I'll give a brief idea on proving this result. So here we want to show that the spectral radius of V is 0. We want to show spectral radius of V, that is supreme of mod lambda in spectrum of V is 0. Spectrum is contained in the closed ball centered at 0 with radius as the spectral radius of the operator. So from that we can say that the spectrum is 0 when we show that spectrum of V is 0, spectral radius of V is 0. But if you just use the definition of the spectral radius in this way, we have to find the spectrum of the operator. But actually we want to find the spectrum of the operator. So for this we want to use the spectral radius formula. Use the spectral radius formula. So spectral radius of V is limit n tends to infinity norm of e power n whole power 1 by n. Here we can show that, so this is a hint to show that norm of v power n is less than or equal to 1 by n factorial for every n bigger than or equal to 1. So if we can show this for every n, we can conclude that by using the spectral radius formula, the spectral radius of V is 0. Okay, so from that we can conclude that spectrum of V is 0. So such an operator we call as a quasi-nilpotent operator. So definition: let T be a bounded operator defined on H, then T is said to be quasi-nilpotent operator if spectrum of T is 0. Okay, so we can easily conclude that every nilpotent operator is quasi-nilpotent, because if you take an nilpotent operator, after some stage T power n is 0 for some n, then spectrum of T power n is 0. Now by applying the spectral mapping theorem, we can conclude that spectrum of T is also 0. Okay, so example is every nilpotent operator is quasi-nilpotent so we have already seen that the Volterra operator is quasi-nilpotent. Okay, so these are the few examples of operators and how to compute a spectrum of the operators. We will be discussing a few more examples in the coming classes, because sometimes we have to use some results to prove to get the spectrum of the operator. So I will stop here. Thank you very much.